Right now, waves are bouncing all around you. Sound waves, gamma waves, and even microwaves are all oscillating in the atmosphere and in your surroundings. A wave is defined as the periodic disturbance that transports energy through a medium. As you can guess, waves transport energy, not matter. Waves are divided into two main types, longitudinal and transverse. Longitudinal waves displace particles parallel to the direction of the wave's motion. The wave's particles do not move with the wave. They actually oscillate back and forth from their individual equilibrium positions. Longitudinal waves have regions of compression and rarefaction. In areas of compression, such as here and here, the wave is pressed into a smaller amount of space, while in areas of rarefaction, here and here, the wave is more spread out. An example of a longitudinal wave is a sound wave. Transverse waves, on the other hand, displace particles perpendicular to the direction that the wave moves. Like longitudinal waves, particles do not move along the wave. Instead, they oscillate above and below their equilibrium positions. Transverse waves, though, have crests and troughs. A crest, right here, here, and here, is the point at which the upward displacement of the wave is at its greatest. Conversely, the trough, here, 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 and right here, is the point when the wave's downward displacement is at its greatest. The middle point, this entire line, between the crest and the trough is the equilibrium. Both types of waves have a few main properties that are used to describe them. First is the amplitude, which is the maximum displacement of a particle from its equilibrium as measured in meters. In longitudinal waves, it is measured from the highest or lowest point to the equilibrium. So the equilibrium would be around right here, and it'd either be from here up to that point, or you could do it from here. And since it has the same height, whether it's a rarefaction or a compression, it doesn't matter which one you use. In transverse waves, it is measured from the equilibrium position to the crest or the trough respectively. So amplitude could be from here to here, or from here down to the trough. Next, wavelength is the length of a wave cycle measured in meters. In longitudinal waves, it is measured as the distance from one compression to the next, or from one rarefaction to the next. So wavelength would be, if you're doing it by rarefaction, would be from here all the way to here, or if you're doing it by compression, would be from here down to here. In transverse waves, this is measured as the distance from one crest to the next crest, or from one trough to the next trough. Again, both ways work. So it could either be from here all the way to here, or from down here to the next trough. A period is measured in seconds and is the time to complete one complete cycle of a wave. So in the time it takes to go one wavelength, that's the period. So it's either from here to here or from here to here, depending on what type of wave you have. Wave frequency is the reciprocal of the period and is the number of vibrational cycles that occur each second. It is measured in hertz. Now that you have all the data types for a wave, you can learn the equation of a wave. Wave speed equals frequency multiplied by the wavelength. Remember that frequency is reciprocal as period, so the equation can also be written as wave speed equals wavelength divided by period. Let's work through an example. If a wave speed is 5 meters per second and its frequency is 1.2 hertz, what is its wavelength? You set up the equation 5 equals 1.2 times the wavelength, and then you isolate the wavelength by dividing by 1.2, and you get wavelength equals 6 meters. Amplitude, wavelength, and frequency are all properties of the wave and are unaffected by a change in the medium. The wave speed, however, is a property of the medium and is affected when the wave experiences a change in the medium. And that's all the basics you need to know about waves.